Work on the super bomber B-36 began in early 1941. The United States was not yet formally at war, but it was actively supplying weapons and equipment to Great Britain, the last island of freedom in Europe. The British had endured the tragic evacuation from Dunkirk and had shown incredible resilience during the Battle of Britain, continuing the fight against the Nazi machine. In a year and a half, the Nazis absorbed almost all of traditional Europe and were preparing to attack their mortal rival, the Soviet Union, and then planned to finish off the stubborn British once and for all. In the Pacific, the Japanese Empire, an ally of the Third Reich in the Far East, was increasingly asserting its ambitions to dominate the region. In America, it was well understood that the country's entry into the World War was only a matter of time. And if events unfolded in the worst possible way, the fall of Britain, the defeat of Russia, or its complete alignment with the Nazis and Japanese expansion, the United States would find itself as a lone fighting fortress, separated from its enemies by thousands of miles of ocean. With that possible development of events, two instruments were vitally necessary for the defense of the country and for striking the aggressors: a powerful Navy and strategic air forces. The Navy already existed. The strategic air forces had to be built from scratch. First and foremost, it was necessary to design and build a huge bomber capable of taking off from American bases, dropping bombs on Germany or Japan, and returning. The situation the United States might face closely resembled what the Soviet Union encountered during the Cold War, when it had to rapidly develop intercontinental strategic aviation. On April 11, 1941, the United States Army Air Forces completed the technical specification for the future intercontinental bomber, an airplane intended to become a true savior of democracy. The military wanted a machine with impressive characteristics: a maximum range of 12,000 miles at an altitude of 25,000 feet, at a cruising speed of 275 miles per hour, a maximum speed at that altitude of 450 miles per hour, and a ceiling over the target of 45,000 feet. For early 1941, these were fantastic requirements. The best American long-range bomber then entering service had a range of only 2,000 miles and far more modest speed and payload capabilities. The new aircraft was conceived as a true intercontinental bomber. Its purpose was to strike from the American continent at strategic targets on other continents. The practical combat radius was to be from 3,700 to 4,350 miles. With such a radius, bomber squadrons could attack any point in Europe, and if based on forward airfields in Canada, in Alaska, on the Hawaiian Islands, and on the Philippine Islands, then any point in Asia as well. The maximum bomb load per the specification was 72,000 pounds, but this reduced the radius. In addition to its primary combat role, a modification of the basic aircraft as a strategic photographic reconnaissance plane was planned. A little later, requirements were developed for a tanker version of the aircraft for carrying fuel and refueling other aircraft in flight. In August 1941, the initial ideas of the American military transformed into a clearer and more realistic concept of 10,000 miles, 10,000 pounds of bombs. The main requirements were formed by imagining a hypothetical bomber obtained by increasing all dimensions of the previous aircraft fourfold. The maximum range of such a machine was to be 10,000 miles, the combat radius with 10,000 pounds of bombs, 4,000 miles, the cruising speed, from 240 to 300 miles per hour, and the ceiling over the target, 40,000 feet. Shortly after the technical assignment for the future super bomber was announced, 4 companies began work on the project: Consolidated, Boeing, Douglas, and Northrop. By October of 1941, the preliminary designs were ready. The winner was Consolidated, which had begun work on the project in May of 1941. The company proposed to build a conventional layout airplane with 6 engines mounted on the wing, using pusher propellers and with 2 vertical tails on the empennage. On the 15th of November 1941, the company received a contract to build 2 experimental long-range bombers. The first aircraft was to be ready in May of 1944, the second by October of the same year. At the request of the Air Corps Engineering Division, the company considered a 4-engine variant with engines mounted in tandem on the wing, but that option did not receive further development. With the United States' entry into the Second World War, military attention turned for a long time to ramping up mass production of existing long-range bombers and to rapidly creating new models. Consequently, work on the new project proceeded slowly, more in a peacetime tempo. During 1942, the model was tested in wind tunnels, and in July and August, a full-scale mock-up of the airplane was assembled at the Fort Worth plant. Combat experience was taken into account during the work. For example, relying on the combat use of earlier aircraft and on British heavy bomber experience, in 1943, designers abandoned the twin-tail empennage and returned to a conventional single vertical tail arrangement. The aircraft was to be fitted with Pratt & Whitney engines called Wasp Major. Thanks to two turbochargers, they delivered 3,000 horsepower at an altitude of 34,500 feet. At the same time, Curtiss was developing new, highly efficient triple-bladed propellers for this bomber. The enormous takeoff weight of the airplane, the gigantic fuselage with pressurized compartments, the large-span wing with integral fuel tanks, and the powerful defensive armament, all of this required a great deal of time for development, testing, and refinement. Taking into account the ongoing war experience, the defensive armament was significantly strengthened compared with previous bombers. It was planned to install aviation guns of 37mm caliber. The total number of heavy machine guns reached 15, grouped in 4 installations. A gun mount with two 37mm guns was to be installed in the nose. The rear hemisphere was to be covered by a mount with one 37mm gun and two 12.7mm machine guns. In mid-1943, the primary characteristics of the airplane were finalized together with the customer. The maximum practical range of 10,000 miles was to be achieved with an empty weight of about 128,000 pounds, a takeoff weight of 265,000 pounds, and a crew of 11. The bomb load corresponded to suspension in bomb bays of 20 bombs of 500 pounds each, when fuel tanks held 18,800 gallons. With a load of 72 bombs of 1,000 pounds each, the fuel supply was reduced to 9,000 gallons, and the range was shortened to 4,660 miles. Maximum speed near the ground was to be 286 miles per hour and 367 miles per hour at an altitude of 29,500 feet. Cruise speed was 242 miles per hour. Service ceiling over the target was 39,700 feet. These figures were later revised. In August of 1945, due to installation of engines of an improved modification, the speed near the ground was specified at 283 miles per hour and 348 miles per hour at an altitude of 29,500 feet. In June of 1943, a strategy conference took place at the Vice President of the United States. Participants concluded that it would not be possible to conduct effective strategic bombing of the Japanese islands using existing long-range bombers. Even taking into account the arrival of the newest aircraft based at airfields in China, it would be necessary to use only air bases very distant from Japan. Consequently, there arose a need to accelerate work on the new bomber. On June 19, 1943, the commander of the United States Army Air Forces, General Arnold, ordered 100 aircraft to be built. On July 23, the Consolidated Vultee Company, also known as Convair, received the contract. After the United States captured the Mariana Islands and established a network of air bases there, the problem of strategic bombing of Japan was solved using other bombers. Work on the new aircraft settled into a slower pace, and the company continued development without particular urgency. Progress was so gradual that by the end of the war, not a single experimental aircraft had been completed. After the end of combat operations in Europe, the United States began reviewing many of its military contracts. Most programs were reduced or canceled entirely. However, the contract with Convair for the production of the B-36 bomber remained in force. The Americans confirmed the order for 100 aircraft. In the future, it was planned to create 4 bomber groups armed with the B-36, which would form part of the new Strategic Air Command. The aircraft received the official designation B-36 and the unofficial name Peacemaker. According to the intentions of the American military and political leadership, the Peacemaker was to become one of the most important instruments for protecting American strategic interests in the post-war world. The B-36 was conceived as a long arm with a nuclear bomb clenched in its fist. This rather ominous image was meant to make the entire post-war world listen more closely to Uncle Sam's opinion. Work on the B-36 continued. By August 1945, the first experimental aircraft at the Convair plant in Fort Worth was 82% complete. In its unfinished state, without some of the equipment and engines, the aircraft was moved on September 8th to the experimental hangar, where assembly and adjustment work continued. The main delays were caused by engine issues. Finally, on June 12th, installation of the engines began, along with ground tests of the power plant. During these tests, the design defects of the propellers were corrected. On July 21st, the aircraft began taxiing runs on the factory airfield. On August 8, 1946, a crew of 9 men led by test pilot Beryl Erickson took the experimental B-36 on its maiden flight, which lasted 37 minutes. During this first flight, the aircraft had a takeoff weight of about 198,000 pounds and carried about 8,000 gallons of fuel. From the beginning of the project to the first flight of the experimental aircraft, 5 years and 3 months had passed. Such a long period was mainly due to the lack of an urgent need for such an aircraft during the Second World War and to the difficulties faced by the Pratt & Whitney Company in developing and refining the engines. It took the company 5 years to bring the experimental engines to an acceptable level of power, altitude performance, and reliability suitable for installation on the test aircraft. For its time, the bomber was a unique engineering achievement in aviation. It was an all-metal monoplane with a high-mounted wing equipped with 6 piston engines installed in nacelles on the wing, each driving a 3-bladed pusher propeller, and featured a tricycle retractable landing gear with a nose wheel. The main design features of the aircraft were determined primarily by the requirement to achieve long range with a sufficiently large payload. At the time of its design and construction, there were virtually no practical alternatives to such a configuration. The potential flying wing design proposed for similar missions was rejected by both the developer and the customer due to a number of unresolved challenges, especially those related to stability and controllability. At that time, there was no possibility to choose a different type of power plant, based on turbojet or turboprop engines. According to the developer's estimates, only powerful piston engines could, under the conditions of fuel efficiency, ensure the creation of an effective bomber with a flight range of about 10,000 miles and a takeoff weight between 265,000 and 330,000 pounds. As for the use of pusher propellers combined with a relatively thick and clean wing, this was explained by the desire to achieve high aerodynamic efficiency during long-range flights with an acceptable cruising speed, while somewhat sacrificing takeoff and landing performance due to the absence of the airflow effect from tractor propellers on the wing. Reducing the drag coefficient of such an aircraft by using a thinner wing would have been irrational, as it would have led to a decrease in lift, an increase in structural weight, and as a result, a reduction in payload and range, contradicting the aircraft's primary purpose. The use of laminar airfoils, in turn, became one of the reasons for choosing the pusher propeller configuration as the most efficient solution. All of the aircraft's equipment and armament were located inside the structure, and the movable gun mounts were retractable. Only the canopy of the forward crew cockpit, the blisters of the aiming stations, and the radome of the radar station protruded from the fuselage. Measures taken to improve both overall and localized aerodynamics made it possible to achieve a high maximum aerodynamic efficiency coefficient, which, according to American data, reached 21, very close to the maximum efficiency value of a flying wing configuration. The large wing area, with a moderate specific loading of about 68 pounds per square foot during takeoff, allowed for the most advantageous long-range flight at relatively low speeds and high altitudes, and therefore with low power consumption. The use of 3-bladed propellers also indicated that maximum range flight was the primary design mode. Preference was given to the slight improvement in propeller efficiency with 3-bladed propellers at this regime compared to 4-bladed ones, which had advantages during takeoff. The power plants and fuel tanks were distributed along the wingspan, which significantly relieved the structural stress on the wing's load-bearing elements, reduced its weight, and freed up fuselage volume for payload accommodation. The reduction of structural weight was also achieved through the use of new, stronger construction materials, metal bonding techniques, and a number of other measures, even replacing the air in the main landing gear tires with helium. The aircraft was designed in accordance with the American strength standards of that period for heavy bombers, which required ultimate operational load limits of plus 3.67 and minus 1. During takeoff, the aircraft could be seriously overloaded, especially considering that the allowable limits were reduced to plus 2 and minus 1. This made its maneuverability extremely limited at the beginning of the flight. Only after a sufficient amount of fuel was burned did the aircraft become lighter, and its structural strength returned to normal values. The airframe structure was fantastically flexible. For example, during a turn, the wingtips could bend by as much as 6.5 feet, about 2 meters. The fuselage also flexed, forming visible bulges near the wing roots. The rather high engine load led to poorer takeoff characteristics. The aircraft accelerated more slowly and climbed less efficiently. Among the structural features, it is worth noting the extensive use of the latest high-strength aluminum and magnesium alloys. Parts made from magnesium alloys accounted for 10% of the airframe's total weight. The use of these materials made it possible to reduce the empty weight of the aircraft by almost 1 ton. Parts of the fuselage skin, the leading edges of the wings and tail surfaces, including both the outer and inner skins of the de-icing ducts, the rear skin of the center section, various reinforcements and air ducts, the bomb bay skin, instrument panels, hydraulic system tanks, engine cowlings, propeller spinners, turrets, and a large number of small components were made of magnesium alloy. In addition, magnesium alloys were used for wheel rims, engine parts, and various equipment elements. The introduction of a new high-strength aluminum alloy made it possible to save more than 6,600 pounds, or 3,000 kilograms, of structural weight. Some general technical solutions also contributed to this reduction. Improvements to the landing gear saved about 2,600 pounds, around 1,180 kilograms. The transition to alternating current saved roughly 2,200 pounds, about 1,000 kilograms, and the use of compartment-type tanks saved more than 6,600 pounds, over 3,000 kilograms, and so on. All these measures made it possible to design an aircraft with an excellent weight-to-payload ratio. For the experimental prototype, the useful load accounted for 58% of the takeoff weight. Later, in serial production, this figure remained roughly at the same level, and by the end of the production run, thanks to a series of targeted improvements, it was further increased. Now let us take a closer look at some of the structural features of the aircraft that defined its unique character and made it possible to achieve the desired results. The wing used special laminar profiles that improved aerodynamics. Near the fuselage, the wing thickness was 22%, and at the tips, 17%. The thicker wing tips were necessary to increase lift and provide greater rigidity in the areas where the ailerons were located. Thanks to the thick profile, the wing could accommodate a large amount of fuel, equipment, and other systems inside. At the wing tips, just ahead of the ailerons, special full-length slots were made. They improved aileron performance. The wing was equipped with slotted flaps that moved backward when deployed. The flaps occupied 42% of the total wingspan and consisted of 3 sections. Each section was positioned between the engine nacelles, which served as partitions for the flap segments. The engine nacelles were placed in the middle of the wing, and thanks to the smooth lines of their junctions with the wing, aerodynamic drag was minimized. The nacelles themselves had a streamlined, elongated shape without any protruding elements. This extended form allowed the installation of oil and air radiators, turbochargers, and other equipment inside the nacelles without increasing their cross-section. In the front part of the wing were the air intakes for the engines. The wing was made of light alloys and consisted of a central section and 2 outer panels. The wing structure had 2 spars and a box-type layout. The box structure carried about 90% of the total load on the wing. The first spar was located at 12% of the chord, and the second at 43%. The height of the first spar near the fuselage was about 5 feet and the second 7.2 feet. The wing box was also used as a fuel tank. Along the entire span, 12 fuel tanks were installed. To reduce stress on the wing, the box was left empty at a distance of 20 feet from the aircraft's center line on each side, so the fuel tanks were shifted toward the wingtips. For proper balance in flight, fuel was first consumed from the tanks located closer to the fuselage. These tanks were not self-sealing, as the fuel in them was to be used on the way to the target. The tanks at the wingtips, however, were self-sealing for protection. Between the fuselage and the wing, partitions were installed to prevent fuel from leaking into the fuselage in case the tanks developed a crack. In the rear section of the wing, behind the second spar, there was a passage connecting to the fuselage. It allowed access to the engines during flight. Along the entire length of the leading edge ran a channel for the anti-icing system, which operated using warm air. The ailerons were equipped with servo balancers. Their structure consisted of a single aluminum alloy spar covered with fabric. The fuselage had a circular cross-section with a diameter of 12.5 feet and a volume of 17,730 cubic feet. Inside the fuselage were the crew compartments, bomb bays, and armament. Structurally, the fuselage was divided into 4 sections: the forward pressurized section containing the front crew cabin, 2 central sections, and the tail section with the second pressurized crew cabin. The total volume of the pressurized cabins was 3,920 cubic feet, while the bomb bays occupied 12,110 cubic feet. The bomb bays were so large that they could accommodate specially designed defensive fighter aircraft. The bomb bay doors were made of magnesium alloy and slid along the outer surface of the fuselage when opened. The crew cabins were connected by a magnesium alloy tunnel 2 feet in diameter and 85 feet long. Inside the tunnel was a small trolley for moving between cabins. The aircraft's tail assembly was cantilevered, all metal, with a single fin and a large dorsal fillet. The design of the fin and stabilizer was similar in its main elements to that of the wing. The leading edges also contained channels for thermal anti-icing devices. The control surfaces were built around a single spar, fabric-covered, and featured axial balance and trim tabs. The flight control system was cable-driven and lacked any power assistance. The control linkage included cable tension regulators and guide pulleys. Creating an effective control system without boosters for such a massive, high-speed aircraft was a truly remarkable engineering achievement that deserves special recognition. The aircraft had retractable landing gear, a tricycle configuration with a steerable nose wheel. The gear extended and retracted hydraulically. The main struts folded backward into the fuselage into a compartment behind the main load-bearing beam. The nose gear could swivel, was pilot-controlled, had twin wheels, and retracted forward into the fuselage. Interestingly, the nose wheel hatch also served as an entry door to the aircraft. The access ladder folded inside the fuselage. Early prototypes were fitted with large single wheels, while production versions used a 4-wheel bogie with smaller wheels. At the tail was an additional retractable support strut designed to protect the aircraft from tail strikes during takeoff. The B-36 was fitted with R-4360 engines, powerful 28-cylinder radial engines with air cooling, the cylinders arranged in a spiral across 4 rows. The first versions of these engines produced at takeoff 3,000 horsepower, but later the power was increased to 3,800 horsepower. Such impressive output became possible thanks to new deflectors that fed cold air to all the cylinders, a new piston ring design, special treatment of the crankcase, an improved reduction gear, new grades of fuel, and a water injection system. Each engine was fitted with 2 turbochargers, which allowed the engines to maintain a rated power of 2,650 horsepower and a combat power of 3,000 horsepower up to an altitude of 34,940 feet. Because the aircraft mainly flew at high altitude in cruise mode, the turbochargers operated at altitude, while at low altitudes they were cut out to simplify the design. Boost then came only from the supercharger. Jet exhaust was not used. At high altitude, all the energy went into the turbochargers, and at low altitude the aircraft hardly ever flew, so complicating the design made no sense. High-altitude flight conditions required the installation of a governor on the engines. Through the reduction gear, the engines drove huge 3-bladed propellers with a diameter of 19 feet and a maximum blade width of 21 inches. The propellers could operate in reverse. When reversed and the engines ran at 75% of rated power, the aircraft's landing roll was reduced by 30%. The blades were made of metal, and an anti-icing system duct was built into the propeller hub. Bomb load options varied depending on range. For this, different types of racks were installed in the bomb bays. There were 4 separate bomb bays on the aircraft. The aircraft could carry 2 bombs of 42,000 pounds each, or 11 bombs of 4,000 pounds, or 28 bombs of 2,000 pounds, or 72 bombs of 1,000 pounds, or even 720 small bombs of 100 pounds. Instead of bombs, the bays could be fitted with cargo or with 4 fuel tanks with a capacity of 3,000 gallons each. The tanks in the fuselage could be connected to the aircraft's fuel system and after their fuel was used, jettisoned. These same tanks were intended to carry fuel when the aircraft was used as a tanker. In addition to conventional bombs, the aircraft could carry various types of nuclear and thermonuclear bombs. All the necessary structural provisions for this were taken into account in the armament system and throughout the aircraft's design. Protecting the B-36 bomber was a real challenge for American engineers. Imagine, this was an enormous aircraft that flew distances so great that no fighter could escort it. In other words, the B-36 had to defend itself. And here was the problem. It was a large, relatively slow machine that could not maneuver quickly. Protecting such a target was very difficult, so unconventional solutions were required. At first, the Americans came up with an interesting idea: place from 1 to 3 of their own fighters inside a bomb bay. The McDonnell Company even received an order for such a special aircraft. The idea was tested in flight. An experimental fighter was attached to the bomber and they tested how it would work. But it quickly became clear that detaching and reattaching the fighter, especially in combat, was extremely difficult. Moreover, such a parasite fighter always lost out to a conventional fighter in performance, since it was designed with many compromises to fit inside the carrier. The idea was abandoned. They then tried another approach: suspend standard production jet fighters under the B-36. Work progressed quite far. Several bombers were even modified to carry suspended fighters, and a series of tests was carried out. But this system also did not perform adequately. In the end, the B-36's defense relied on conventional gun installations with 20mm aviation cannons and on electronic warfare systems. There were proposals to arm the aircraft with air-to-air guided missiles, but those plans did not proceed beyond initial designs. The bomber version's crew consisted of 15 people, 3 pilots, 4 navigators who could also serve as bombardiers or radar operators, 2 flight engineers, 2 radio operators, and 4 gunners. On long-range flights, the crew could be increased to 18 members by adding reserve personnel. All of them were accommodated in 2 pressurized cabins. One of the flight engineers was permanently stationed in the rear cabin near the aiming station, monitoring the landing gear, flaps, engines, and propellers, and informing the pilot about the start and end of takeoff and landing. In the forward cabin, on the upper level, sat 2 pilots. Behind them, facing the side of the aircraft, was the senior flight engineer in charge of engine control. The radio operator was located on the middle level behind the engineer, while on the lower level worked the bombardiers with their radars and the navigator. In the rear cabin, along with the engineer, there were always 2 gunners on duty, while the rest of the crew could rest. There were 6 beds installed for that purpose. The reconnaissance versions had a different crew composition. From all this, it becomes clear that to achieve the maximum flight range, the Americans had to sacrifice other characteristics, primarily speed, rate of climb, and takeoff distance, which was further increased because the propellers did not blow over the wing. Later, a number of design changes were made to improve these characteristics, but all of them came at the cost of reducing flight range. The experimental bomber XB-36 underwent intensive flight tests from the end of 1946 to the beginning of 1947. In total, the aircraft completed 31 flights with a combined duration of 89 hours. During testing, numerous structural deficiencies were revealed, which required serious modifications to the design. The engine cooling system, which had caused overheating at altitudes above 36,000 feet, was improved. Tests also showed the need to radically redesign the layout of the forward crew cabin and replace part of the fuselage skin. On the XB-36, each main landing gear leg had a giant wheel with a diameter of 110 inches. Such landing gear imposed enormous loads on runways, so during flight trials at the factory airfield, a special concrete strip had to be built, 17 inches thick at the edges, increasing to 27 inches at the center. This drastically limited the number of airfields capable of operating the B-36. It was therefore decided that the production models would switch to 4-wheel bogies with much smaller wheels, reducing the ground pressure and expanding the number of airfields able to accommodate these super bombers. During tests, problems arose from mutual vibrations between the power units, propellers, and wings. Because of this, there were in-flight failures in the propulsion systems, including propeller destruction and engine shutdowns. On March 15, 1947, during the 15th flight, the right landing gear failed to deploy before landing. Of the 12 crew members, all but 2 parachuted to safety. The aircraft commander and co-pilot remained aboard, continuing flight for 6 hours until the fuel was exhausted. They then performed a careful landing, saving the aircraft. After completion of the test program, the B-36 was upgraded to bring it closer to the production B-36 standard. It received four-wheel landing bogies, new engines, a reinforced and refined airframe, and additional equipment. In this improved form, the B-36 resumed flights in June 1948. In 1950, it was used for testing a tracked landing gear system specifically developed for the B-36. These trials took place in the spring of 1950, but the design never entered widespread use, neither on the B-36 nor on any other heavy aircraft. Later, until the late 1950s, this aircraft was used for training flights and then as a transport plane. Some of the refinements resulting from the B-36 flight tests were implemented by Convair on the second prototype, the B-36. The main assembly work on it was completed in April 1947, after which it was moved to the experimental hangar, where modifications to the aircraft's structure continued until winter. Like the B-36, the B-36 carried no defensive armament and used single-wheel main landing gear struts. The B-36 differed from the first aircraft by the shape of the forward cockpit canopy, which extended beyond the fuselage contours. Connectors were introduced into the wing and fuselage structure, engines with improved turbochargers were installed, and a radar station was mounted. On December 4, 1947, the crew of Bernice Erickson made the first flight of the B-36. After completing its test program, the B-36 was converted to the RB-36E standard and entered service with the Air Force. The first production aircraft was the B-36A, initially intended for ground testing at Wright Field. This plane was not planned to be airworthy, but its enormous size made it impossible to deliver its parts to Wright Field by ordinary transport. Therefore, it was decided to make the aircraft fully flyable. On August 28th, it made its first flight, and on August 30th, it flew to Wright Field, where it underwent an extensive testing program, 45 different tests in total. This first B-36A received an improved crew cabin and a four-wheel landing gear with wheels measuring 56.7 inches in diameter. After it, an entire series of such aircraft was produced. The serial production of the B-36 expanded extremely slowly. Preparations for manufacturing had begun as early as the end of 1943, but since the prototype had not yet been built, real preparations started much later. Mass production in noticeable quantities, 2 to 4 aircraft per month, was launched only in 1948. By May 1948, only 10 B-36A aircraft had been built. By August 1948, 27 aircraft had been completed, of which 22 were A-series machines. At that time, the Air Force had accepted only 13 aircraft of this series. In September 1948, Convair management took measures to expand production at the Fort Worth plant. The number of workers increased from 7,000 to 13,400, and a 10-hour workday was introduced. Thanks to these measures, by October, 35 aircraft had been completed, 12 of the B-series, 22 of the A-series, and 1 prototype. By April 1, 1949, the plant had produced 54 B-36 aircraft, and the workforce had grown to 18,000 people. The government-owned aviation plant in Fort Worth, Texas, was leased by Convair. And before the B-36, it had been used for serial production of the long-range B-32 Dominator bombers. Transitioning to the new, far more complex aircraft required a complete reorganization and re-equipment of the production facilities. As of August 1949, the total expenditure on the B-36 production program amounted to about $1 billion. The sum included the costs for the first 95 B-36B aircraft, and 75 new orders for D and E series planes. The cost of the project and the prototype amounted to $26 million. The cost of preparing serial production was $16 million. The work performed by the Convair company amounted to only about $400 million, or 41.8% of the total program cost. Convair paid for the raw materials and supplies itself, while the United States Air Force paid the remaining cost of the B-36 aircraft directly to subcontractor companies. In the overall cost of the plane, the airframe accounted for 42%, the engines for 23%, the propellers for 6%, and the armament, equipment, and instruments for 29%. Under the first order, each B-36B cost $4,692,000. However, the installation of 4 turbojet engines, the K-1 bombing system, and other modifications increased the price to $6 million, $248,000. The D-Series aircraft already cost $4,732,000. The final cost of the B-36J, the last modification in serial production, was $3,776,000 in 1954. The cost reduction was achieved by increasing the total number of B-36s produced to nearly 383 aircraft, modernizing the plane's structure, systems, and equipment, and improving manufacturing technology to reduce production expenses. The labor intensity of producing the prototype was 1,600,000 man-hours. The first serial aircraft required 500,000 man-hours, which was later reduced to 100,000 man-hours. In addition to the parts, assemblies, and components supplied by subcontractors and the United States Air Force, the plant in Fort Worth produced 68,000 parts for the B-36. Serial production was equipped with 2,000 machines and 87,000 units of special tools. The final assembly line for the B-36 received 8,500 sub-assemblies and completed aircraft components. Some parts of the B-36 required machine tools of such large size that they had never before been used in American aircraft manufacturing. The first 12 experimental aircraft were primarily intended for training flight crews and ground technical personnel. They had no defensive armament. Later aircraft were produced in combat configuration and differed in equipment composition. Soon, all the early machines were brought up to combat standard. In total, 22 such aircraft were built, of which 21 were later converted into reconnaissance planes. All these bombers were equipped with engines rated at 3,000 horsepower, and they began to receive navigation radar. The first 4 aircraft were delivered to the Air Force in June 1948. They arrived at Eglin Air Base for testing under real conditions. 6 aircraft were received in July and 5 in August. All the planes were assigned to the 7th Heavy Bombardment Group of the 8th Air Force, based at Carswell Air Base in Texas. Soon, long-range flights of the new machines began, during which the crews practiced operational techniques and handling of the aircraft. On April 8th to 9th, 1948, a production aircraft made a flight lasting 32 hours over a distance of 6,090 miles with a 10,000-pound bomb load that was dropped roughly at the midpoint of the route. The average speed of the flight was 190 miles per hour. The flight was conducted with 2 engines shut down. On May 13th to 14th, 1948, an aircraft with full armament and ammunition flew 8,000 miles in 36 hours with a bomb load of 10,000 pounds. The bombs were dropped at the halfway point of the route, and the average speed was 223 miles per hour. On June 29, 1948, during a flight from Fort Worth to Muroc and back, 2,900 miles, a bomb load weighing 83,770 pounds was dropped from the aircraft. One bomb weighing 41,890 pounds was released from an altitude of 35,000 feet. The second bomb from an altitude of 40,000 feet. The average speed of the flight was over 248 miles per hour. On June 30th, 1948, a bomb load weighing 71,870 pounds was dropped from the aircraft. On July 18th to 19th, 1948, the aircraft flew 6,000 miles, the maximum range of another type of bomber, mostly at an altitude of 29,500 feet, with an average speed of 301 miles per hour, which exceeded the average speed of that other aircraft. The takeoff weight on this flight reached 310,850 pounds, and the takeoff run was 5,580 feet. In March 1949, the aircraft reached an altitude of 45,930 feet. Flights at altitudes above 39,370 feet lasted 12 hours. 2 such flights were carried out. During these high-altitude flights, many pieces of equipment failed because temperatures in the compartments dropped to minus 43 degrees. In service, these aircraft provided the following principal characteristics. At a takeoff weight of 317,460 pounds with a fuel load of 24,040 gallons and a bomb load of 10,000 pounds, the tactical radius when flying at an altitude of 8,200 feet was 3,880 miles. With a bomb load of 72,310 pounds, the tactical radius was 2,110 miles. With a full fuel load exceeding 26,420 gallons and without a bomb load, the maximum range was 9,130 miles. with an operational combat weight of 211,640 pounds at an altitude of 31,500 feet over the target. The maximum speed was 332 miles per hour. The first full-fledged bomber of the B-36 series to enter service with the United States Strategic Air Command was the B-36B. The principal difference from the previous model was the installation of a full complement of defensive armament. On board were fitted 16 20mm guns installed in remotely controlled turrets. In the rear installation, 2 guns were mounted linked to a targeting radar with an ammunition load of 600 rounds per barrel. The remaining guns were installed in twin turrets. 2 retractable turrets at the base of the fin were controlled from the aiming station in the rear of the fuselage from above. 2 retractable turrets in the tail lower section were controlled from the lower aiming station. 2 retractable turrets above, behind the pilot's cabin, were controlled from the forward aiming station. In addition, 2 guns were installed in the nose of the fuselage with an ammunition load of 400 rounds per barrel. The B-36B was fitted with modernized engines having a maximum takeoff power of 3,500 horsepower, which allowed an increase of maximum speed to 381 miles per hour at an altitude of 34,500 feet, and a ceiling in the target area with combat weight up to 42,650 feet. The radar was replaced with an improved model. The bomber was adapted for a wide range of calibers and types of conventional bombs, including 2 bombs weighing 41,890 pounds. With capacious bomb bays and a large payload capacity, the B-36B became the carrier of the first American air-transportable thermonuclear bombs, weighing up to 44,090 pounds. Other bombs from the American nuclear arsenal could also be employed from the aircraft. The maximum bomb load reached 85,980 pounds when the takeoff weight was increased to 357,480 pounds. The overall increase in the B-36B's takeoff weight due to the installation of standard armament and additional equipment was compensated by the increased takeoff power of the new engines. The first aircraft made its first flight on July 8, 1948. After trials and modifications, the B-36B series went into production at the end of the year. A total of 73 aircraft of this modification were built, and almost all of them were later converted into B-36D models. In November, the B-36B began to reach the 7th Bombardment Group, and soon the formation of the 11th Bombardment Group began. The new modification of the aircraft was mastered fairly quickly, and already on December 7th and 8th, 1948, one of the B-36B flew 8,000 miles from Texas to Hawaii and back, dropping 10,010 pounds of bombs halfway through the route. The duration of the flight was 35 hours 30 minutes, with an average speed of 239 miles per hour. On March 12, 1949, a B-36B taking off from Fort Worth flew 9,600 miles in 43 hours 37 minutes. A bomb load weighing 10,010 pounds was released 25 hours after takeoff. After landing, there was fuel left in the tanks for 2 hours of flight. For the greater part of the flight, 2 engines had been shut down. On June 24 and 25, 1949, a B-36B completed a flight of 7,000 miles, of which 6,000 miles were flown at an altitude of 40,025 feet, with an average speed of 300 miles per hour. In one of the flights, a B-36B flew at 48,000 feet. All these flights of fully equipped and armed B-36B convincingly demonstrated that the United States had acquired a powerful strategic means of nuclear deterrence. In the summer of 1950, the Korean War began, the first open combat clash between the forces of the Communist East and the forces of Western democracies. In December 1950, Strategic Air Command had 2 heavy bombardment groups with 38 B-36 aircraft and 1 strategic reconnaissance group with 20 aircraft. In addition, the command included 12 medium bomb groups and 3 medium strategic groups, which had 542 aircraft in service. From this enormous strategic air potential, only 5 groups were deployed to Korea. The rest of the aircraft remained in strategic reserve and were ready, if necessary, to unleash their power against the Eastern Bloc. In March 1947, Convair proposed a new version of the B-36 bomber with an unusual configuration: tractor propellers. This variant was designated B-36C. The main feature was 6 powerful combined engines, each producing from 4,300 to 4,500 horsepower. In September of the same year, the decision was made. The last 34 aircraft out of the first 100 ordered B-36s would be produced in this new configuration. A full-scale mock-up of the wing with the new engines was even built, and preparations were underway for serial production. But things did not go according to plan. Development of the combined engine encountered a host of technical problems. By April 1948, it became clear that the new engine would not be ready in the near future. At the same time, the international situation worsened. In June 1948, the Soviet Union began the Berlin blockade. The American military decided not to wait. Bomber forces had to be expanded quickly. Therefore, all the aircraft that had been planned as B-36C were ultimately produced in the B-36B configuration. According to design calculations, the B-36C would have had impressive characteristics: a maximum speed of 410 miles per hour, the ability to bomb targets at 45,100 feet, and a flight range with 10,000 pounds of bombs of 10,000 miles. Strengthening the bomber's defensive armament or adding escort fighters created a new problem. The aircraft became heavier, and it became increasingly difficult for it to take off. Moreover, even better armament could not protect it from an attack by a large group of enemy fighters. To truly improve the B-36's ability to reach its target, more radical solutions were needed. Above all, increasing speed and altitude. Then a brilliant idea appeared. Why not add jet engines? They would not only increase speed and altitude, but also ease the takeoff of the heavy bomber. In October 1948, Convair proposed this idea to the military. It was decided to first test the concept on one production B-36B. They chose the 54th aircraft and installed 4 jet engines on it. They mounted them in pairs under the wings on special pylons, the same arrangement used on the B-47 bomber. The first flight of this experimental airplane, which was designated YB-36D, took place on March 26, 1949. Tests produced decent results: maximum speed at an altitude of 35,000 feet, 400 miles per hour, service ceiling 40,000 feet. However, combat radius decreased slightly to 3,530 miles compared with 4,300 miles for a standard B-36B. After the initial tests, the airplane was upgraded. 4 new, more powerful jet engines were installed. Each produced about 6,000 pounds of thrust. The pylons for them were also taken from production B-47s. Trials were successful, and the type entered production under the designation B-36D. At the same time, the reconnaissance version, RB-36D, began to be produced. Moreover, practically all already produced B-36B aircraft were converted to B-36D. The first batch of 7 airplanes rolled off the assembly line in December 1949. These were RB-36D reconnaissance aircraft. The last B-36D bomber left the line in June 1951. In total, 24 new B-36D were built, and an additional 59 were converted from older B-36B. The first B-36B arrived for modification at the San Diego plant in April 1951, and by November, it had been reworked. The last aircraft was converted in February 1952. In addition to the jet engines, the B-36D received upgraded equipment. A new bombing and navigation system was installed. The first airplanes had one type of radar gun sight for the tail installation, which was later replaced with a more advanced unit. The electronic countermeasures suite was also improved. The additional jet engines and new equipment significantly increased the combat power of the production B-36. This heavy bomber became an even more fearsome weapon in the Cold War. Almost simultaneously with production of the B-36D bomber, series production of its reconnaissance variant RB-36D began. The first aircraft converted into a strategic reconnaissance platform was a B-36B. It made its first flight on December 18, 1949, still without the additional jet engines. After trials and installation of the jet engines, the airplane became the first reconnaissance aircraft of the RB-36D standard. This first strategic reconnaissance airplane was demonstrated to President Harry Truman on the ground and in flight at Eglin Air Force Base on April 22, 1950. In June, this airplane was handed over to the 28th Reconnaissance Wing. The reconnaissance version was equipped with 14 aerial cameras of various types. Their number was later increased to 23. The total weight of all photographic equipment was about 3,000 pounds. The cameras were installed in the forward bomb bay. In the second bay, 80 photographic bomblets were carried, and in the third bay, an auxiliary fuel tank with a capacity of 292 gallons was installed. The fourth bay housed signals intelligence and electronic warfare equipment, the antennas of which in radio-transparent fairings projected beyond the fuselage contours. The standard radar was also used for reconnaissance. The aircraft crew was increased to 18 people, to 22 during extended flights. The composition included 2 pilots, a flight engineer, a photo navigator, a radar operator, a radio systems operator, a photo technician, 3 operators of radio intelligence systems, and 7 gunners. In total, 24 production B-36D reconnaissance aircraft were built. Also, 21 B-36A bombers and 1 experimental aircraft were converted into B-36E reconnaissance types. In terms of equipment and main characteristics, they corresponded to the B-36D. The first aircraft entered conversion on February 28, 1949, and made its first flight as an B-36E on July 7, 1950. The last B-36E was completed on July 20, 1951. The flight characteristics of the reconnaissance variants differed virtually not at all from those of the base bombers. The appearance of more powerful new engine variants contributed to the further improvement of the flight characteristics of the B-36. The engine of the new modification, whose maximum power increased to 3,800 horsepower, allowed a modest improvement in speed and service ceiling. The new engines were installed on a production aircraft that was released under the designation B-36F. The aircraft with the new engines made its first flight on November 11, 1950. The installation of the new engines allowed the maximum speed to be increased to 416 miles per hour. The altitude over the target at a takeoff weight of 265,000 pounds reached 44,000 feet. The cruise speed with the new engines became 235 miles per hour. In addition to the power plant improvements, the aircraft's radio-electronic equipment was modernized. A new bombardment radar system and a targeting radar were installed, which became standard for the B-36 beginning in April 1950. A new radar transparent radome was also introduced. In total, by November 1951, 34 production B-36F bombers had been built. On the basis of the B-36F, a strategic reconnaissance version, the B-36F, was created. Its standard crew was increased to 22, and new reconnaissance radio-electronic equipment was installed. The main flight characteristics of the reconnaissance version were close to those of the bomber. For example, at a takeoff weight of 265,000 pounds, the B-36F reached a maximum speed of 410 miles per hour. The next version of the aircraft was the B-36H bomber. The first flight of this model took place on April 5, 1952. The new machine differed from the previous version mainly by improved targeting equipment. A modernization of the bombing system was carried out under the program Blue Square. Thanks to modern electronics, it was possible to significantly reduce the size and weight of the system's units, and to simplify operation in flight and during maintenance. The workspace of the second flight engineer was also improved, and a more effective radar system for the tailgun installation was installed. The maximum speed of the B-36H was 416 miles per hour, and the altitude over the target was 44,000 feet. As in the previous case, a reconnaissance version, the B-36H, with the same equipment was released together with the bomber. In total, from May 1952 to July 1953, the Convair plant produced 83 bombers and 73 reconnaissance aircraft of this model. 3 B-36H aircraft were converted between 1953 and 1955 into special planes for testing cruise missiles and were later used as bomber tankers. The last production bomber was the B-36J. In this version, the fuel capacity in the wings was increased by 2,770 gallons, while the takeoff weight rose to 410,000 pounds and the maximum bomb load was set at 72,000 pounds. The maximum speed with an operational weight of 172,000 pounds was 410 miles per hour. The first flight of the B-36J took place on September 3, 1953. A month later, the new machines began to enter combat units. In total, by August 1954, 33 B-36J bombers had been built. The last 14 aircraft, which were being built at the Fort Worth plant, were modernized during production under a weight reduction program called Featherweight. The aim of the project was the further increase of speed, ceiling, and range of the production aircraft. two weight reduction options were proposed: remove all defensive armament from the aircraft and reduce the bomber crew to 13 people, the program Class W2, or reduce the crew to 13 people and leave only the tailgun installation, Class W. The second option was adopted. The first Leighton B-36J was released on February 11, 1954, and production of the series was completed in August. In addition to producing new B-36J aircraft, by December 31, 1954, earlier models were upgraded, each receiving updated service designations. At the same time, reconnaissance variants were also modernized, with the crew reduced from 22 to 19 members. The effectiveness of the weight reduction can be seen in the changes to the B-36J's characteristics. The empty weight decreased from 180,000 pounds to 166,000 pounds, while the maximum takeoff weight remained the same, 410,000 pounds. The combat radius increased from 3,420 miles to 3,990 miles. Maximum speed rose to 416 miles per hour at an altitude of 36,400 feet, and the bombing altitude reached 44,600 feet. Earlier and lighter variants, after modernization, achieved a maximum speed of 417 miles per hour and a ceiling of 47,000 feet. The cost of a single aircraft in the final modification reached $3,776,000. The last production B-36J aircraft were equipped with 6 piston engines generating 3,800 horsepower for takeoff with water injection and 2,800 horsepower in nominal mode, plus 4 jet engines producing 5,990 pounds of thrust at takeoff and 4,730 pounds in nominal mode. The maximum fuel capacity was 36,400 gallons. The final production B-36 strategic bomber was completed on August 10, 1954, and arrived at Loring Air Force Base in the state of Maine 4 days later. This marked the end of B-36 mass production. In total, 383 aircraft were built, along with 2 experimental variants featuring swept wings and 8 jet engines. By 1953, the Strategic Air Command of the United States included 6 wings of heavy bombers and 4 wings of heavy strategic reconnaissance aircraft equipped with B-36s. By the end of 1954, after production had ended, a modernization program was approved to upgrade all early B-36 models to the standard of the final production series. This process was completed by April 1957. In October 1955, the 4 reconnaissance wings were reclassified as bomber wings. All reconnaissance aircraft were converted into bombers, though they retained the capability for rapid reconversion into reconnaissance configuration. In December 1954, within 10 wings of the Strategic Air Command, there were 209 B-36 bombers and 133 RB-36 reconnaissance aircraft. In addition, the command included 24 wings of medium bombers and 5 wings of medium reconnaissance aircraft, operating 795 B-47s, 265 RB-47s, 78 B-50s, and 12 RB-50s. All medium-class aircraft were equipped with aerial refueling systems, allowing them to perform strategic missions over intercontinental distances. In 1955, the Strategic Air Command began receiving the first jet-powered intercontinental strategic bombers, the Boeing B-52. The first B-52s entered service with 3 wings that had previously operated B-36 and RB-36 aircraft. By the end of 1956, the number of B-36s in service had decreased to 247 aircraft. By the end of the following year, only 127 B-36s remained operational. The final year of B-36 service was 1958. On February 12, 1959, the last B-36 was officially retired. Thus ended the era of piston-engine strategic bombers in the United States Air Force. At the peak of its strength, the Strategic Air Command's B-36 fleet was distributed among the following units as of October 1, 1955. 2nd Air Force, headquartered at Barksdale Air Force Base, Louisiana. Its structure included the 72nd Bombardment Wing at Ramey Air Force Base, Puerto Rico, with 3 squadrons, as well as the 19th Air Division at Carswell Air Force Base, Texas, which comprised the 7th Bombardment Wing with 3 squadrons and the 11th Bombardment Wing, also with 3 squadrons. 8th Air Force, headquartered at Westover Air Force Base, Massachusetts. It included the 45th Air Division at Loring Air Force Base, Maine, with the 42nd Bombardment Wing consisting of 3 squadrons. 15th Air Force, headquartered at March Air Force Base, California. The composition included the 28th Bombardment Wing at Ellsworth Air Force Base, South Dakota, with 3 squadrons. It also included the 14th Air Division at Travis Air Force Base, California, which contained the 5th Bombardment Wing with 3 squadrons. The 47th Air Division at Walker Air Force Base, New Mexico, included the 6th Bombardment Wing with 3 squadrons. The 57th Air Division at Fairchild Air Force Base, Washington, included the 92nd Bombardment Wing with 3 squadrons and the 99th Bombardment Wing, also with 3 squadrons. The 810th Air Division at Biggs Air Force Base, Texas, included the 95th Bombardment Wing with 3 squadrons. Interesting fact, originally one bombardment group had 18 B-36 aircraft, 6 in each squadron. Later, the number of aircraft in a wing was increased to 30. 10 aircraft per squadron. Pilots cleared to fly the B-36 had to be very experienced. They were required to have logged at least 1,000 hours on 4-engine aircraft, of which no fewer than 600 hours had to be on the B-29. But that was not all. Each pilot also completed an additional 50 hours of indoctrination on the B-36 itself. At first, he simply observed how experienced pilots operated the airplane, and only then was he allowed to take the controls. To train B-36 crews, the Americans converted 11 B-50A aircraft into trainer machines designated TB-50A. On them, crews practiced the handling techniques for heavy bombers, saving wear on the far more expensive B-36 and its engines. And interestingly, despite its gigantic size and enormous weight, and even without hydraulic boosters in the control system, American pilots considered the B-36 a pilot's airplane. In plain terms, it was relatively easy to fly. The work of a B-36 crew required high qualifications and serious engineering preparation. Imagine, a 30-man ground crew prepared the aircraft for flight, and then the crew themselves spent more than 1 hour simply inspecting the aircraft, starting the engines, and warming them up. When the B-36 began to enter the Air Force, it became clear that existing airfield equipment was simply not suitable for such a giant. This seriously degraded the aircraft's combat capabilities. Refueling, bomb suspension, inspections, and other operations took a very long time. The U.S. Air Force did not even have sufficiently powerful tugs to tow these aircraft to the runway and to parking positions. It was necessary to design and manufacture a lot of new airfield equipment specifically to match the B-36's characteristics. Special dollies were produced for transporting large bombs with unique hoists rated at 49,600 pounds and 22,000 pounds. They were designed to transport and suspend super-heavy aerial bombs. For example, a bomb weighing 41,800 pounds measured 26 feet in length and 4.6 feet in diameter. The movable hoist rated at 49,600 pounds could lift the bomb from the ground, deliver it to the aircraft, raise it to a height of 12.5 feet, rotate it 360 degrees in any direction, shift it laterally from center by 4 inches, move it forward or backward by 10 inches, and even tilt it longitudinally by plus or minus 6 degrees. The hoist was powered by an electro-hydraulic system. The hoist, rated at 22,000 pounds, could perform all the same operations and was identical in design. To speed up bomb loading, a special 4-wheel dolly rated at 14,000 pounds was designed to be attached directly inside the bomb bay. 6 such dollies were used at the same time for loading. A special all-wheel drive airfield tug was designed for towing the B-36. Because of their enormous size, the B-36 aircraft were stored and serviced in the open air without any hangars. To make the work of the technical personnel easier during bad weather, the Convair company produced special docks, lightweight frame structures covered with canvas. They supplied compressed air and electricity inside, had stationary lighting and mobile heaters. Later, the company developed a collapsible stationary dock hangar into which a B-36 could be moved in or out in just 15 minutes. All of this was extremely important because soon the B-36s began to be transferred from their comfortable bases in Texas, California, and other warm places to forward airfields in Alaska and Greenland, where the climate was much colder and far less hospitable. The issue of airfields suitable for operating the B-36 bomber was very pressing. The Air Force had to urgently begin modernizing existing airfields in August 1949, when the Navy and its lobby in Congress seriously criticized the B-36 program. Representatives of the United States Air Force stated that there were 57 airfields on the American continent from which fully loaded B-36s could take off, and another 109 such airbases existed in other parts of the world. With a landing weight of about 198,000 pounds, the B-36 could also land at 285 additional airfields in the United States. Thus, a wide network of operational airbases for the B-36 was established all around the world. A decade of B-36 operation showed that it was a fairly reliable and safe machine. The greatest losses of the Strategic Air Command occurred during the first 2 years of service, when the aircraft were being mastered and refined. During that period, 9 aircraft were lost and 70 people died. 1 aircraft was lost in a collision with an F-51 fighter in April 1951. In combat units, the first serious incident occurred on September 15, 1949. During climb after takeoff, the automation system on one B-36 accidentally switched the propellers into reverse, and the aircraft, losing speed, crashed into a lake. All crew members were rescued, the aircraft was recovered, repaired, and returned to service. On February 14th, one of the B-36s made a water landing after an engine fire in the strait near Queen Charlotte Island, off the west coast of Canada, and sank. The crew of 17 men took to life rafts. Rescue ships picked up 12 people, while 5 were never found. In a crash near Newfoundland on March 18, 1953, another aircraft was lost, and all 23 crew members, including General Richard E. Ellsworth, perished. There were several more flight incidents of varying severity. Particularly dramatic were the crashes after takeoff, when several dozen tons of aluminum and magnesium alloys soaked in burning gasoline came down to the ground. All of it burned for a long time, producing an effect similar to a giant incendiary bomb. Such disasters occurred on May 28, 1952, and November 16, 1956, near Denver. But the most devastating blow to the B-36 units of the Strategic Air Command came from nature itself. On September 1, 1952, a powerful hurricane struck the Carswell Air Force Base in Texas, where rows of B-36s from 2 bomber groups stood on the tarmac. More than 70 aircraft were damaged. At that time, half of all B-36s in Strategic Air Command service. 51 aircraft were repaired by Air Force maintenance units and returned to duty by October 5th, while 26 had to be sent back to the manufacturer for restoration. As we have already said, in the early 1950s, the United States Strategic Air Command had at its disposal 4 fully ready bomber groups equipped with B-36 aircraft. These machines had ultimately become the backbone of America's nuclear deterrent. All bomber units were permanently based on the territory of the United States, but when the international situation intensified, the aircraft were launched into the air and flown to forward air bases scattered around the world, closer to targets on the territory of the Soviet Union and its allies. Large redeployments of bombers to forward lines began in August 1953, immediately after the end of the Korean War. The objective was simple: to deter any possible attempts by the Communists to start a new military conflict. At that time, aircraft from Fairchild Air Force Base flew to Guam and Okinawa. In 1954, bombers from all Strategic Command units began rotational flights based at the island of Guam, and thereafter at Andersen Air Force Base, these aircraft were present almost continuously. The American High Command considered various options for delivering strategic strikes against the territory of the Soviet Union from northern air bases along the shortest polar routes, including paths across the Arctic. To implement global plans for the use of bombers that would allow nuclear fire to cover practically the entire territory of a potential adversary. The aircraft began to be based as close as possible to the northern latitudes. In 1954, during Operation Northern Star, bombers were transferred for the first time to Eielson Air Force Base in Alaska near Fairbanks. Afterwards, they began to be permanently based at the base near Thule on the island of Greenland. In the harsh polar cold and during polar nights, the aircraft themselves, the maintenance system, flight and technical crews, and the entire complement of Strategic Command units underwent a severe test of professional skill and endurance during ground and flight operations in the circumpolar regions. One of the main contentious issues during the creation and deployment of these bombers was their survivability against modern air defense systems. The appearance in service with the Soviet Air Forces of the near-sonic MiG-15 aircraft with their powerful onboard armament, as well as the deployment of a network of Soviet radar stations capable of detecting comparatively slow-moving bombers long before their approach to the target, called into question the ability of these aircraft to survive in combat. When assessing defensive capabilities, the following assumptions were made. Fighter escort over such great distances was impossible, and the aircraft would meet air defenses only in the target area, where its takeoff weight would be reduced and it would have a more or less acceptable speed and altitude. That last assumption was valid only for raids from bases in the United States against targets located in Europe and in the far eastern areas of the communist bloc. For strikes against targets located deep in the interior, bombers taking off from forward bases would have to encounter air defense forces at much earlier stages of the flight, when the aircraft still carried an almost full fuel load. Hence the search for shorter routes to distant targets across the Arctic, with the additional use of the factor of seasonal polar night to complicate the actions of interceptor fighters. For the United States Air Force and for the American aviation industry, the problem of bomber survivability was a constant headache. The result was continuous efforts to increase aircraft speed, to improve the effectiveness of bomber defensive systems, and the constant study and adoption of new methods of combat employment. Attempting to assess the real picture with the possibility of interception even by near-sonic fighters, the United States Army Air Forces conducted numerous tactical trials of intercepting an airplane flying at very high altitudes, about 40,000 feet, by fighters whose performance characteristics were similar to those of the Soviet MiG-15. Experienced Air Force pilots took part in the tests, but their attacks were mostly unsuccessful. American Sabre fighters managed to attack the B-36 only with a precise approach into its tail. To get into the bomber's tail, a fighter flying on a different heading had to make a turn. The turning radius at that altitude amounted to 5.5 to 8 miles, which meant the fighter had to begin the maneuver at a distance of 15 to 18 miles from the bomber. But at that range, it is very difficult to determine the target's heading and speed, so in most cases, the fighters simply flew past at a large distance from the B-36. Had the Soviet MiG-15s been used instead, less maneuverable in the horizontal plane and equipped with an imperfect aiming system, the chances of spoiling the attack would have been even higher. After these trials, the Air Force Chief of Staff, General Vandenberg, stated confidently, "Tests have shown that the B-36 bomber cannot be intercepted by contemporary fighters at altitudes above 30,000 feet, and the difficulty of interception increases with flight altitude. Even a slight turn by the bomber would break off a fighter's attack, and it was very hard to resume it. A B-36 that is at an altitude above 30,000 feet and 150 miles from the target, the detection range of the early warning radars of that time, at a speed of 310 miles per hour will reach the target in less than half an hour, and there is no guarantee that fighters will be able to intercept it in that time." All these calculations were quite convincing and largely valid for the early 1950s. Later, when supersonic high-altitude interceptor fighters armed with air-to-air guided missiles entered air defense forces, when the first surface-to-air missile systems appeared, and when the detection ranges of ground and airborne radars increased significantly, the possibility of a B-36 breaking through to the target fell sharply. And the era of the last piston-engine superbomber came to an end. However, the most powerful attack the B-36 had to withstand did not come from Soviet MiGs, but from American legislators and the perennial rival of the United States Air Force, the United States Navy. In July 1949, the United States House of Representatives formed a commission to investigate the circumstances surrounding the awarding and modification of B-36 contracts and Air Force policy on strategic bombing aviation in general. The campaign was initiated by the Navy with the help of a powerful lobby in the Pentagon and among legislators. The Navy sought to redirect billion-dollar investments from strategic bomber contracts into the construction of modern aircraft carriers capable of carrying fast jet bombers and attack aircraft, carriers of nuclear weapons. In this noble struggle for national interests, the aircraft's disinterested opponents naturally received support from other American aircraft manufacturers whose interests were harmed by B-36 orders. The commission questioned a number of senior Air Force officers, executives of several aircraft companies whose interests were affected by the B-36 contracts, and representatives of naval aviation who were the main opponents of the Air Force on this issue. During the investigation, the opponents of the B-36 did not point to any previously unknown negative qualities of the airplane. They mainly criticized the aircraft's purpose and used well-known performance figures as arguments. Some of the old opponents of the B-36, including the former commander of the United States Strategic Bombing Forces, General Kenny, told the commission that they had revised their assessment of the airplane. The results of flight tactical tests confirmed its good qualities, production of the aircraft was organized, and this dispelled their doubts about the technical feasibility of serial production of such machines. General Smith, Deputy Chief of the U.S. Air Force Production Programs Division, stated in his testimony that at Wright Field Air Base, a comparison of the characteristics of several bombers was conducted: the B-36, B-50, B-54, and the jet-powered B-49. The results revealed an interesting picture. The average speed of the B-36 over a route equal to the maximum range of the B-50 turned out to be higher than the speed of the B-50 itself. Moreover, the B-36 could fly higher. Compared to the B-54, the performance of the B-36B modification was superior in almost every respect except speed over the target. However, the B-36D modification, with its jet engines engaged, achieved even greater speed over the target than the B-54. The B-36 was also recognized as a more advanced platform for use as a strategic reconnaissance aircraft than the Northrop B-49, particularly in terms of stability and flight range. General Curtis LeMay, Deputy Chief of Staff of the U.S. Air Force, declared in his testimony that the B-36 was capable of reaching targets anywhere on the globe. He also stated that this bomber could perform raids not only during the day but also at night. According to him, at that time there were still no fighters capable of successfully attacking bombers flying at an altitude of 40,000 feet at night. LeMay also claimed that the B-36 at 40,000 feet operated beyond the range of the ground-based radars of that era. Moreover, bombing from such altitude could be carried out with high accuracy using the new radar bombs. After lengthy discussions and mutual accusations between supporters and opponents of the B-36, the aircraft and its advocates ultimately prevailed. The Commission approved the actions of the U.S. Air Force leadership regarding the orders for the B-36. However, mindful of the heated Senate hearings, the Air Force Command decided that when discussing the budget for 1950 to 1951, it would note that the planned increase in orders for the B-36 would be the last. This was because the following year, more advanced aircraft of the same class with jet engines were expected to appear, namely the first experimental strategic jet bombers, the B-52 and B-60, whose characteristics were to surpass those of the B-36 significantly. In addition to the serially produced bomber and reconnaissance versions of the B-36, which were built in several modifications, a number of experimental and prototype versions of the aircraft were developed. During their design, testing, and refinement, numerous challenges were addressed. Challenges that were essential for the further development of the concept of heavy and super heavy aircraft, particularly those of strategic aviation. The B-36 was an all-metal, high-wing monoplane of classical design with a single vertical fin and retractable landing gear. On long-distance flights, the aircraft's crew could number up to 18 people. The fuselage had a circular cross-section, 12 feet 6 inches in diameter and 162 feet 9 inches long. Structurally, it was divided into 6 compartments. At the front was the pressurized crew cabin, followed by an unpressurized gun compartment, then a bomb bay 69 feet 3 inches long, followed by the rear gun compartment, the aft pressurized gunner's cabin, and finally, the unpressurized tail section. The load-bearing structure of the B-36 fuselage was unique. Through the central section of the fuselage ran 2 powerful beams above and below, connected by a system of struts and braces made of duralumin tubing into 2 truss frames. The outer skin, which covered them, together with the frames and stringers, served mainly for shaping and for absorbing local aerodynamic loads. The remaining fuselage sections featured a semi-monocoque design. The forward crew cabin was 2-tiered. On the upper level sat 2 pilots side by side. Behind them was the station of the flight engineer. On some aircraft, 2 engineers, seated facing the rear of the aircraft and able to monitor the engines. In the ceiling was an astronomical observation hatch with a glass dome, which could be jettisoned in case of an emergency landing. Along the rear wall of the cabin, on both sides, were the gunners' positions with glass turrets and gun sights. On the lower deck, there were the positions of the navigator bombardier and the nose gunner. Above them was an unpressurized compartment for the cannon mount. Further behind was the radio operator's station. The cockpit was separated from the middle section of the fuselage by a flat, pressurized bulkhead with 2 hatches. The right one led to the gun compartment, and beyond that, to the bomb bay. The left one opened into a pressurized tunnel, 24 inches in diameter, leading to the rear pressurized cabin. To move through this tunnel, the crew used a small trolley with a hand winch. Beneath the cockpit was a niche for the front landing gear strut. In its forward wall was an entry hatch that could be used when the nose gear was extended. Above the niche, on both sides, there were emergency hatches. Next came the bomb bay, where between the structural frames and the outer skin of the fuselage were located the aircraft's general systems: cylinders with oxygen, air, and water, various pipelines, and electrical cables. The external skin of the compartment was made of magnesium alloys, with only the upper section made of duralumin. Behind the bomb bay was the compartment for the rear gun turrets. Its design was similar to the forward one, except that it housed 4 retractable turrets, 2 on top and 2 underneath. The rear pressurized cabin was located behind the turret compartment. At the workstations of the gunners operating the tail turrets, there were 4 glass domes. During an emergency landing, all domes could be jettisoned and the sights moved aside. Additionally, there was an emergency hatch in the lower part of the cabin, which could be used as an entry point while the aircraft was on the ground. In addition to the 4 sighting stations, the tail cabin contained the control post for the tail radar and the rear gun installation. A camera could be mounted in the cabin floor to record bombing results. The cabin was also equipped with bunks for crew rest, a refrigerator, a stove for heating food, a wash basin, and a toilet. Later, most of this domestic equipment was removed to reduce the aircraft's weight. The aircraft's tail section had a semi-monocoque structure and was unpressurized. The tail assembly was attached to it, and at the very end was the tail gun mount. The main material of the tail section was magnesium alloy. The wing was of a box spar type with 2 main spars and an additional wall. The wing's transverse structure was formed by assembled truss ribs. The main material of the wing box was high-strength aluminum alloys. The lower skin panels between the outer and inner engines were removable for the installation and servicing of fuel tanks. The wing root had a chord of 33.5 feet, the tip 11.2 feet, a dihedral angle of +2 degrees, and an incidence angle of +3 minutes. The airfoil was laminar, with a relative thickness of 22% at the root and 17% at the tip. Along the trailing edge of the wing were retractable 3-section flaps with electric actuation. The fabric-covered ailerons were fitted with servo tabs, providing full mass balance and internal aerodynamic compensation. On the leading edge of the wing were the air intakes for the engine cooling systems, oil radiators, air supply for the anti-icing system, and the air conditioning system. The leading edge panels between the air intakes were removable. They had double skin with hot air flowing between the layers to prevent icing. At the wingtips were vents for hot air discharge and navigation lights. In the rear part of the wing, there was a passageway for in-flight engine inspection. The tail assembly consisted of several elements: the fin, forward section, the main fin, and the stabilizer. The leading edges of these parts were heated with air to prevent icing. The elevators and rudders were fabric-covered and equipped with a special balancing system to ease control forces. On the control surfaces, 2 types of auxiliary tabs were installed: servo tabs closer to the aircraft's center and trim tabs farther from it. The section of the skin between the front structural element of the fin and the forward wall of the forward fin support was made of 3-layer panels. At the base of the trailing edge of the fin, there was a fairing that housed radar units controlling the tailgun turret. At the top of the fin stood antennas for the radio stations and the LORAN navigation system. 2 cable antennas for communication were attached to the leading edge of the fin, while another cable antenna was mounted on the forward fin support. The aircraft's landing gear had 3 struts, including a steerable nose 1. Early versions were also equipped with a tail skid that could retract into the fuselage. However, during operation, it turned out that the aircraft did not touch the runway with this skid upon landing, so it was abandoned in later versions. All flaps and wheel brakes were hydraulically operated. The wheels on the left and right main struts could be braked independently, which made taxiing easier on the ground. In the final modification of the bomber, the landing gear was reinforced because of the increased takeoff weight, though outwardly it looked the same. The nose strut had two wheels 52 inches in diameter, and its rotating cylinder also acted as a shock absorber. The strut retracted forward into the fuselage in the direction of flight. The main struts had four wheels each, 57 inches in diameter, and retracted into the wing, moving toward the fuselage. In the folded position, they were locked by mechanical latches with hydraulic actuators. The shock absorber worked on oil and helium mounted below to the rear wheel console and above to a special balancing lever on the strut. The other end of the lever was connected by a rod to the front console. Thus, one shock absorber served both wheel consoles. The power plant included 6 Pratt & Whitney Wasp major air-cooled piston engines. These were radial engines with 28 cylinders. Early versions of the aircraft were fitted with engines producing 3,000 horsepower during takeoff. Later versions were upgraded with engines rated at 3,500 horsepower. The most advanced variants received engines producing 3,800 horsepower during takeoff. Such power was achieved not only through the large displacement of the engine, nearly 19 gallons, but also through an intense operating cycle. The boost pressure exceeded 2 atmospheres at takeoff and was slightly lower at the design altitude of 35,000 feet. The boost was provided by a centrifugal supercharger and 2 turbochargers, which maintained a nominal engine output of 2,650 horsepower and a combat power of 3,000 horsepower up to an altitude of 35,000 feet. A measure of the technical perfection of this engine was its characteristics: a weight of about 3,370 pounds at an operating shaft speed of 2,700 revolutions per minute. To improve cooling, especially on the ground, special fans were installed in the air ducts in front of the engines. A special skirt was placed between the engine nacelle and the propeller spinner to regulate the airflow. The exhaust gases were used as efficiently as possible. They powered the turbochargers, heated air for the anti-icing system, and were employed in the neutral gas system used to pressurize the fuel tanks. The engines drove enormous 3-bladed propellers about 19 feet in diameter. These propellers were made of strong aluminum alloy and contained internal channels through which hot air circulated to prevent icing during flight. The fuel tanks were located in the wings of the aircraft. The total fuel capacity was nearly 33,600 gallons. The tanks were protected by a special coating, except those between the inner engines. Fuel from these tanks was used first, so by the time the aircraft approached the target, they were already empty. Later models added additional tanks in the outer wing sections, providing another 2,770 gallons of capacity. To increase speed and altitude over the target, the aircraft was additionally fitted with 4 jet engines. Each produced about 5,200 pounds of thrust. The flight control system was mechanical. The only electric actuators operated in the autopilot, which was used mainly during cruise flight. Therefore, all control surfaces had special compensators and trim tabs, which eased the pilot's work and reduced the forces on the control columns. The onboard equipment consisted of hydraulic and electrical systems that powered numerous mechanisms throughout the aircraft. There was also navigation, aiming, radio communication, lighting, domestic, oxygen, and rescue equipment on board. In addition, a fire suppression system, an anti-icing protection system, and air conditioning in the pressurized crew cabins were operational. The B-36 had the most powerful artillery armament of any bomber in the history of aviation. It consisted of 8 twin mountings with 20mm cannons. Each cannon could fire about 800 rounds per minute, and the shells flew at 2,400 feet per second. The mountings provided fire in all directions. Each mounting was operated by a separate gunner with his own optical aiming station. The tail mounting was operated by a gunner operator who also worked with the radar. The nose mounting could cover a horizontal sector of 30 degrees, and the barrels depressed by 30 degrees upward and by 28.5 degrees downward. The ammunition load was 400 rounds per gun barrel. The fuselage turrets were retractable and arranged in pairs. The barrels of these turrets could swing away from the fuselage by 70 degrees and toward the fuselage by 20 degrees. Horizontally, the turrets rotated through 180 degrees. The ammunition load was 600 rounds per barrel. When the turrets retracted, the barrels became parallel to the fuselage, and the resulting opening was closed by a cover that slid along the skin. The turret drive was electric. The tail gun installation was located in a hemispherical fairing. The barrels depressed by 45 degrees horizontally and by 40 degrees vertically. The ammunition load was 400 rounds per gun barrel. In lightened versions of the aircraft, the nose and tail installations were removed. All upper turrets were taken off, and the number of gunners was reduced by 2. Radar stations were used to control the fire of the tail installation. Early models had a radar with a single antenna above the guns. Later versions were fitted with a more advanced station with 2 antennas side by side. Sometimes each antenna had its own protective cover, and sometimes the cover was shared. Some aircraft carried an electronic countermeasure station and devices for dispensing metal strips that confused enemy radars.